Okay, so to remind you, what is the utility of a thermodynamic description? Well, in the real world, we have an awful large number of particles in any small volume. For example, 10 to the 23 particles is a mole, and a mole can very easily fit within a cubic centimeter. And we could, of course, follow the system or study its evolution by using the equations of Newton and taking into account the positions and the momenta and the accelerations if there are interactions between the particles, and determine where the system or how the system is going to evolve in time. But with so many particles, that's really impossible to do. They have such a system, in fact, a formalism, which is called molecular dynamics. But in molecular dynamics, they consider only the molecule that they're interested in, and maybe a few water molecules. So they have a limited number of particles. So maybe they could go up to maybe 1,000 particles, would be about maximum now, I think, for the computing calculations. And they could describe the system microscopically. And that gives you all the information. For example, if you wanted to know the temperature, you would just divide the kinetic energy of each particle by the number of degrees of freedom in the system. That would give you the temperature. But it is much more effective and more reasonable to do macroscopic thermodynamic study of the system. So as long as, for example, the interactions between the particles are not too strong, so we have something which is approaching an ideal gas, and that the particles are point-like, that is basically saying the same thing, that the interactions are not too strong, then we can use this thermodynamic formalism, which deals with a much lower number of variables. So for example, we have the energy, the entropy, the volume, temperature, the pressure of the system. These are what are known as a coordinate description in terms of these thermodynamic variables, instead of the coordinate description in terms of the individual positions and momentums of all the particles in the system. So the utility of this thermodynamic description is that you can go to a much lower number of variables. And it turns out that as long as you have a system which approaches an ideal gas, which is not exactly an ideal gas, but one which approaches an ideal gas, then this system of coordinates is sufficient to determine almost everything you want to know about the system, at least at a macroscopic level. So this is the first chapter of Prigogine, which is titled Conservation of Mass. I'm not going to go into the whole chapter. I'm just going to go over some of the most important or basic concepts of this chapter. So we start with a well-defined geometrical volume. For example, in these ecospheres, it has a volume defined by the glass layer, okay, of macroscopic dimensions. So we have at least 10 to 23 particles in the system. And we can talk about three different types of systems: isolated systems, in which there is no energy, no matter, or no work exchanged between the system and its environment. That is an isolated system. These systems, of course, don't exist in nature. They're only an idealization of what you could think of in nature. We also have closed systems where we do allow exchange of energy, but no matter and no work performed over the system. So this in fact would be like these ecospheres where light is allowed to come into the system. So we do have an exchange of energy in the system, and infrared light can leave the system in the form of heat. And we also consider open systems, in which they are open to energy, matter, and work exchange between the system and the environment. So, for example, we have a question: what type of thermodynamic system is the planet Earth? Does any one of you want to respond to that? Is it an isolated system? Is it a closed system? Or is it an open system?
I think that it's an open system because the Earth exchange energy and matter with the space.
Yes,
No?
okay. It's a open system because the matter, of course, is coming in through meteorites and dust, which is settling down on the surface of Earth. But if we ignore the matter exchange with space, then we could more or less approximate it as a closed system. So we have energy coming in, but no work being performed on the system, and no matter or very little matter being exchanged. So it's really an open system, but we can sometimes also approximate it as a closed system. Okay, what type of thermodynamic system is the universe?
I think the same about the universe,
Yes,
because it's
we don't really know. That's a difficult question. You
yeah,
a lot of theories
and
of parallel universes and the possibility of going one to the other. So then it would have to be an open system. But who knows?
and
That is all speculation.
yes, and in the nature there exist real closed systems, or everything is open system. Because
Um,
I remember that in thermodynamics, everything that we work has
yeah.
with closed systems or isolated systems, but in nature there is possible.
Well, for example, what about this ecosphere? I think you would have to assume that that was a closed system because we don't allow any matter to go through the system. Maybe there would, no? For example, maybe hydrogen molecules can infiltrate the glass and get into the system, or helium, better helium molecules, which are less interactive. For example, there are helium leak detectors. So any small groove or opening on the material will allow helium to flow through it. But I guess this is a good approximation, no? Something like this, even though it's not exactly from nature, well, it is from humans, which are part of nature, but you wouldn't find exactly something like this in nature, no? So you're right, most of the systems are really open systems, and thermodynamics really only deals with isolated systems or closed systems. But in fact, we have to take into account the exchange of matter in most systems. So, and that is the point of classical irreversible thermodynamic theory of Prigogine, is to move from isolated or closed systems to open systems, treat open systems with a formalism which is similar to that of closed systems. So these ecospheres, then I'm just giving you them again because I find them very interesting. I would love to get one as a present for a birthday. If anybody can find these, I'll even pay extra for it. I've been looking for them, but they don't exist. I guess you have to order them from online. But they are systems which are closed, so it's completely closed. And you only have to keep them at a certain temperature and under light, daylight. And they have shrimps, and they have cyanobacteria, and they have algae and other kinds of microorganisms within the system. And it's like an ecosystem, a small ecosystem. And apparently these shrimps can live for about 10 or 11 years. So they have ecosystems, I see these ecospheres, which are still alive after 10 or 11 years. So you still see the shrimp swimming about without ever having to give them any food. So it'd be a very good present for a young person also. So they have a pet that they don't really have to take care of. Just make sure that temperature doesn't change too much and that the system is receiving sunlight. Okay, so in thermodynamics, we talk about two types of variables. One are known as extensive and the other are intensive, or properties of the system. The extensive properties or variables are defined by the system as a whole. For example, the energy, the volume, and the number of moles. And these are additive. So we know the energy in one part of the system and in the other part, and the sum of the two gives us the total energy. So they're always additive in this sense. And the number of moles the same and the volume the same. But there are also intensive properties, and these take on well-defined values at each point in the system. And some examples are temperature, pressure, and chemical potential. So we'll see how these variables, these intensive variables, are in fact related to the extensive variables in the following. And the thermodynamic system is described by what is known as a fundamental relation. So that fundamental relation says everything about the system in terms of these macroscopic variables, which are extensive, like the energy, the volume, number of moles, etc. For example, if you have a spin here, you would need the angular momentum of the system. You could have more variables depending on how many degrees of freedom you allow in your system. So you have an entropy representation and also an energy representation. So if we take the entropy representation, we can write an equation which relates all of these variables just by doing an extension, a transformation of ds, that's change in the entropy. It's just partial s with respect to partial E, the energy, constant volume and number of moles, times dE, plus partial s by partial v, at constant energy and number of moles, times dV, the volume, plus partial s by partial n, the number of moles of substance, at constant energy and volume, times dN, and so on, if you have more variables defining the system. So now these ratios, or these partial derivatives of the different extensive variables, give rise to these intensive variables. So partial S by partial E at constant volume and number of moles is just 1 over the temperature. And partial S by partial V at constant energy and number of moles is just the pressure over the temperature. And partial S, with respect to partial N at constant E and V is just minus the chemical potential over the temperature. Okay, so that is how the intensive variables, temperature, pressure, chemical potentials, are related to the extensive variables of the system. So this is equilibrium thermodynamics. We assume that this Gibbs equation is just an expansion in partial derivatives of the variables. So this is valid. And we assume that also when we go out of equilibrium, that we also have the Gibbs equation, which is valid.
So now we want to go.
Oh, sorry. Let me kill that because I had it. Okay. This here I have to turn off. Okay. Let me see if I have any more of those here. Be right back with you. It's also quartile. Okay. Sorry about that. We're getting there.
Don't worry, no problem.
Okay. Should have checked this before. No? Okay, let me go back. And put it in full view. Okay. So now if we want to consider a system with more than one chemical element, okay, so in this case, we have a multi-component system, then we have to include the sum over the different chemical potentials of the different molecules in the system over the temperature times dN, which is, this is, N here is the molar fraction, the number of moles of substance gamma over the total number of moles in the system. So this again is just the Gibbs equation, but in the case that we have a multi-component system, where these mu are defined as the chemical potentials, and we can see that from this expansion, this is just mu is equal to minus T times partial S with respect to partial N gamma, at constant energy volume, and all other mole numbers being held constant. So that's what this prime on this N gamma means, that all the other mole numbers are held constant. And we're only varying the number of moles of substance gamma in the system. So as I mentioned, chemical potentials are intensive variables. And just like the other partial derivatives of the entropy, for example, 1 over the temperature, just partial S by partial E, and the pressure over the temperature, just partial S by partial V. This comes from the expansion of the Gibbs equation here. So the chemical potential can also be expressed in other ways, for example, in the entropy representation. So this was the case for the Gibbs equation. This is the entropy representation, but also we can write the system equally in terms of in the what's called the entropy representation, how the energy representation, how the energy depends on these extensive variables. And in that case, we can write the chemical potentials as partial E, that's the internal energy, with respect to the variation in the number of moles of substance gamma, holding the entropy, the volume, and all the other mole numbers constant. And we can also introduce what is known as the enthalpy, which is just the internal energy plus the pressure times the volume, or the Helmholtz free energy, which is the energy minus the temperature times the entropy.
Teacher?
Yes?
In the differential equation system that you showed before,
yeah, in the Gibbs equation?
No. In the last part of class, about the chemical reactions.
Yes.
I remember that que aparecen unas Fs y unas Hs. Esas son
Unos que,
the Helmholtz leaders, F and H. There's represent the Helmholtz enthalpy and...
No, in fact, for chemical reactions which are occurring in the laboratory,
yes,
what we have constant are the pressure and the temperature. Those are
yes,
the things we can hold constant. So then we really have to use the Gibbs free energy. So that's G.
In the differential equation system, they appear terms like F and H. Yes, that's correct.
But those are referring to labels for the different chemical components. They were not referring to the free energies. Entonces,
okay.
For example, H was not the enthalpy. H was the number of or the molar concentration of hydrogen cyanide.
Yes.
Okay, and F was formamidic acid. Oh no, that's Fa, formamide. I think F represented formamide. So that's a different. Yeah, sorry for confusing you then.
Yes, I'm sorry for the confusion. Yes, when I see the I saw the differential system. I thought that mean the Helmholtz and enthalpy.
No,
I'm wrong. Sorry.
That was another labeling system. It's different than this when we're talking about the free energies. No? So we can define a number of free energies which allow us in equilibrium thermodynamics to determine the evolution of the system. For example, if we do have the pressure and temperature constant in the system, then we can use the Gibbs free energy, and we optimize that, or that means we minimize actually the Gibbs free energy, and that allows us to determine the evolution of the system. Okay, and in case of the Helmholtz free energy, that is a constant temperature and volume. So each of these different free energies represent different conditions. And each of these can be taken as an optimization principle. That is, we minimize these in order to determine the evolution of the system, where the system is going to go. And we can, of course, write the chemical potentials or all the other intensive variables in terms of the different energies in the system, in terms of the enthalpy, or in terms of the Helmholtz free energy or the Gibbs free energy. Okay, so, but what do these chemical potentials in fact look like? Well, here I mentioned that they were like the partial derivatives of the extensive variables. For example, the entropy with respect to the number of moles of substance gamma, or the partial of the energy with respect to the number of moles of substance gamma, holding different variables constant. But what they actually look like is that for ideal systems, that means systems which are interacting as point-like particles and that don't have an extension in space, then we can write the chemical potential as some function zeta. Okay, this is the chemical potential of a substance gamma. So it's some function zeta of pressure and temperature plus R times T. R is the universal gas constant, and T is the temperature, times the log of the molar fraction. This big N gamma is equal to the number of moles of substance gamma over the number of moles of the system, the total number of moles of the system. So this goes between 0 and 1, this big N gamma. So this is what the chemical potentials look like in reality for ideal systems. But now, for example, for the ideal gas, the zeta function can also be separated into two functions, one which only depends on the pressure and the other which only depends on the temperature. Okay, so these are different functions, eta, and this is the logarithm of the pressure and the gas constant times the temperature. That's the case for ideal gases. We can divide this component here into two parts also, each depending on different variable, the pressure and the temperature. But for non-ideal systems, so that is systems in which the particles are interacting between them, we can still write an equation similar to this, but now we have to include what is known as an activity coefficient. So this measures like the interaction between the particles. So this is how the chemical potentials depend for systems which are non-ideal. Okay. Now, to go back to the entropy, okay, this comes from this Greek word, which actually means evolution. And if you can, these are the letters in Greek alphabet here, which if you pronounce it like they pronounce it, then you get the word entropy, which means evolution, which in fact is a good meaning for this variable in thermodynamics, because it in fact describes through the second law of thermodynamics the evolution of the system. And it is an extensive property of the system. Remember, that means that the total is the sum of its parts. So for instance, when we have an open system, then the change in entropy of the system can be due to a change or an exchange with the environment, external environment, and that's why this sub-indice E here is written, and due to a second component which depends on the irreversible processes which are occurring within the system. So this is the internal production of entropy due to irreversible processes in the system. So because it's an extensive variable, we can just sum the two and that gives us the total. Now, for the case of reversible processes, which of course do not occur in nature, but if we have an idealized system where we have only reversible processes occurring, then DIS is equal to 0. But for any irreversible process, DIS has to be greater than or equal to 0. That's the second law of thermodynamics. And now if we take an isolated system, then this part goes to 0. We don't have any exchange of entropy with the external environment. So the change in entropy of the system is just equal to the change in entropy due to internal irreversible processes which are occurring within the system. And this, as I mentioned, has to be greater than 0, is equal to 0 only in the case of reversible processes. And we have ds is equal to dis, which has to be greater than or equal to 0, and that's just the second law of thermodynamics. Okay, I have some more material here below, but I can't read it because I have this bar which goes over the screen, which doesn't allow me to see it. So I'll just go on to the next slide and hope I didn't miss anything important there. So let's take an example. So this is the case of the entropy production due to the flow of heat. And we're going to consider this continuous system. So this is the case where we have, in fact, the system is composed of two parts. One which is maintained at temperature T1 and the other one at T2. And let's assume that T1 is less than T2. So we have a higher temperature in this region than in this region. So we know that there's going to be a flow of heat from the high temperature system to the low temperature part of the system. So this is what is represented by this irreversible process, which is the flow of heat, diq by dt. And that's going into system 1. So that's why we write this 1 here as the super indice. Okay, so this is the flow. Remember that for the production of entropy, we have a force times a flow. So this is the force, 1 over T1 minus 1 over T2. And this is the flow of heat. And that gives us the entropy production. This has to be greater than 0 by the second law of thermodynamics. So this is the case of the discrete system, where we have just two boxes, one at temperature T2 and the other one at temperature T1, where T2 is greater than T1, and this gives us flow of heat and the entropy production due to the flow of heat. But we can also have a continuous system. For example, we could have a metal bar which is separating these two boxes, and so the temperature along the bar can change as a function of position. And that's why instead of 1 over T1 minus 1 over T2, we have, in fact, the gradient of the temperature as a function of position on the bar, which is connecting the two. So this is the case of a continuous system. This is the entropy production for the continuous system. And W here is the flow of heat. And it has a super indice I, which corresponds to the three coordinate variables of the system, so x, y, and z. So we have a volume in three-dimensional space. And so this corresponds to the flow of heat in the x, and the y, and the z directions. And this is the derivative or the gradient of the temperature in those three directions, and over t squared, okay? The t squared comes in because it's really, this is the gradient of 1 over the temperature, and the gradient of 1 over the temperature gives you the gradient of temperature over t squared. We have a minus sign here to ensure that the flow of heat is always from the warmer to the colder system. So that was the entropy production due to the flow of heat. Now, what about in the case of the diffusion of material? So here, we're looking at, again, this continuous system, some system here, but which has a chemical potential, which is different. So for example, it could be a concentration of a particular element gamma. Okay, this is the subindice gamma. It could be a different concentration, because you remember here when I told you that the chemical potentials depend on the molar fractions. So this big N gamma, which is really dependent on the concentration of the system. So then we have, here we have mu1 over T1, which corresponds to the chemical potential of the temperature in this subsystem, and minus mu2 over T2, which corresponds to the chemical potential over the temperature in this subsystem, times the flow of material. Okay, so this is the flow of material into system 1, and it would be coming from system 2, which is considered here as the external environment of system 1. So that's why it's written as d subindice E and 1 gamma by dt. So this is the flow of material, and this is the force. This is the force due to the chemical potentials or the affinities of the system. We'll see how these are related, the chemical potentials to the affinities, in a moment. And this is the case for the discontinuous system. But in the case that we have a continuous system, which we have no division between the two, but we have different concentrations of the materials on the different side, then we have this gradient of concentration, of the gradient of the chemical potential, which depends on the concentration over the temperature. Okay, and we have times the flow of matter. This is the density or the mass per unit volume of substance gamma, and this delta represents its net velocity with respect to the center of mass velocity of the system. Okay, so we always take it into account, the center of mass velocity of the system, and this gives us the rate of the diffusion of substance gamma with respect to the center of mass of the system. Okay, and we also have another component which is due to any external force of the system. For example, a material can carry a charge with it, an electrical charge. And so if you have an electrical field over the system, then you can also get a movement of the material due to the electrical force acting on the charges of the material. And so you have to include that also into account in the flow, okay? And this comes in here to the force of the system. This is the electrical force, which is over the system in the three components, X, Y, and Z, and over all of the components in the system. And if we sum that all up, that gives us the entropy production due to the diffusion process, which can be a natural diffusion without any external forces, then this would go to zero. But if we have the materials with charge on them, then we have to include, if we have an electric field over the system, this force, this is the Coulomb force due to the movement of charge. Now we also have another irreversible process, which is known as chemical reactions, okay? And these are just equal to the affinities over the temperature times the velocities or the rates of the reaction that gives rise to the production of entropy due to chemical reactions which are occurring in the system. So all of these entropy productions have to be greater than zero because they correspond to irreversible processes which are occurring. First one is the flow of heat and the flow of material, and this is the chemical reactions which are occurring in the system. Okay, so in general, we can always write the production of entropy as a sum of all the flows and the forces. These are generalized flows and forces. So for example, the flow of heat is J, and the force is the gradient of 1 over the temperature. And for the chemical potentials, this flow is the flow of matter, and this force is mu1 over T1 minus mu2 over T2. And for the chemical reactions, the flow is the rate of the reaction, and the force is the affinity over the temperature. And we'll show that the affinities are related to the chemical potentials. We can also have interference of irreversible processes as long as we maintain certain symmetry constraints. So for example, we cannot have a scalar force giving rise to a vector flow, for example. So we have to observe the symmetry constraints. And if we observe the symmetry constraints, then we can have a coupling of different irreversible processes. Now, when at least we're close to equilibrium, if we're not too far from equilibrium, then these generalized flows here, the J's, are linearly proportional to the generalized forces. At least that's an approximation that you can use for when you're very close to equilibrium. So in the case that we have a coupling of two different processes, then the flow of, let's say, one irreversible process, whether it's the flow of heat or the flow of matter or the chemical reaction rate, is related in a linear manner to the forces of the other two processes which are occurring within the system. So for instance, this x1 could be the gradient of the temperature. No? This could be the flow of matter, which is proportional to the gradient of the temperature and the gradient of the concentration, for example. Okay, so we can have a coupling of material coupling due to the flow of heat, due to the gradient of the temperature, and we can have a flow of material due to the gradient of concentration. So therefore, we have coupling of these two irreversible processes occurring. And these are just coefficients. They're known as the Onsager coefficients, which are taken as constants in the case of a linear coupling. So this is a linear approximation when we're near to equilibrium. And the same for the second process. The flow for the second process is just equal to these Onsager coupling constants times the force of irreversible process 1 plus another coupling constant times the force of irreversible process 2. And so now if we write the production of entropy using these values here and then multiplying by the forces, then we get an equation of this form. Okay. And we know that the entropy production has to be positive definite. So that puts various restrictions on these coupling constants. For example, L11, the Onsager coupling coefficient L11, which is known as a proper coefficient because it corresponds, for example, if this is the flow of material, this corresponds to the mu1 over T1 times mu2 over T2, the force. And so this has to be greater than 0 in order for this equation to remain positive definite for whatever values of the forces here. We're taking the forces as the variables here. So for whatever these values, we know that the production of entropy has to be positive definite. So that puts, if you can see this relation that these have to be positive definite, the proper coefficients of Onsager. And between the mixed coefficients, these L12 and L21, these only have to satisfy this relation, that L12 plus L21 squared has to be less than 4 times L11 times L22. So we get that from assuming we have linear relations between two irreversible processes which are coupled, and that the entropy production has to be positive definite. So that gives us particular values of these